Welcome everyone, and so this is the fifth day, I think, and we're having Milind Sohoni for a talk entitled "Geometric Complexity Theory: Lie algebraic methods for projective closures." So you can start whenever you're ready.
Okay, so I'll start now. So thank you very much, the organizers for this talk series. Am I audible? Am I clearly audible?
Yeah.
Yeah. Okay. So thank you all very much for organizing this talk series and for giving me this platform. So I'm going to talk about GCT, Lie algebraic methods for projective closures. So this is joint work with Bharat and KV, and it's also appeared recently in Archive uh, about a month ago. So this is my talk outline today. So I'm going to talk about some preliminaries, group action, and I'll pose the stabilizer question. Then the big picture, what GCT looks like, and for the stabilizer question, what does the structure of the problem and parts. These are the two areas of our contributions. Then I'm going to talk about the local model, which is a Luna type model for a point for a group action. Then we will apply the local model to forms and look at limits, basically limits of forms being acted upon by one's parameter family. So how do stabilizers change under taking limits? And then we will look at this apply it to the codimension 1 case when the closures of orbits are of codimension 1. So by the way, this is all under projective and affine closures both. Then we will close the arguments we had made, Bharat had made 2 days ago about one matrix under conjugation and projective closures under and the action of one parameter subgroup. And then we look at some advanced topics, the very local stabilizer and its connection with the algebra cohomology. And section 9 of the archive paper is really about future directions, optimization and differential geometry. So please do stop me if there are any questions. So of course, group G is connected, reductive, algebraic group over complex numbers. And there's a representation rho from G to NV, which is rational, typically polynomial. And for a point y, the orbit of y is of course G dot y, G acting on y for all G. And of course, OY need not be, the orbit need not be closed, but it's always constructible. The simplest example are, if you look at GLN acting on CN and a non-zero vector, then the orbit is the whole CN minus 0 and the closure includes point 0. Or if you look at matrices and acted up under the adjoint or the conjugacy action, then, and if I look at the top nilpotent JN, then its closure, of course, is the whole nilpotent cone for the conjugate action. So really, our question is that given 2 points, x and y, in this G module, is x in the closure of y, right? And in the projective space, if x and y are projective, treated as projective points, then is x in the projective orbit closure of y. So these are of course of direct relevance to algebraic complexity theory, and typically these both x and y have very distinctive stabilizers. So the big picture, of course, is that we have x and y, and there's a G action and through one parameter subgroup, and when lambda t acts on y, and we have the weight space decomposition, then x is the leading term, and then the question really is that how do I connect the stabilizers of y and x? So under this one parameter family. So this is the quintessential example, and the basic example coming from GCT is then when we have a large matrix, n by n matrix, and y is the point determinant, and x is the point permanent of a smaller matrix, homogenized homogenized to make it the same degree. And we in fact know that for a given m there is a large n, so that x does in fact appear as a leading term of y. So we know that this happens, and we also know that the stabilizer, for example, or the determinant is a reductive group, while that of this homogenized permanent has a huge nilpotent part and has a core which is reductive. So really the question is that is there a homogeneous substitution in the determinant which will give us a smaller permanent. So the point really is that stabilizers change dramatically under taking limits. So so in the GCT arena, there's it's the question is in the negation. What evidence or what sort of certificate or obstructions are there to prove that there is no such one parameter subgroup which will take the determinant to a given permanent, right? And we must answer the question when x and y have very distinctive stabilizers. So the GCT approach has been the distinctive stabilizers. The GCT sort of thesis is that the distinctive stabilizers is adequate information. I think Christian Ickenmeyer's talk 2 days ago also made the same point, and that the projective orbit closure actually makes we have a surjection C of in the homogeneous coordinate ring surjects onto the homogeneous coordinates of y, and that gives you the space for obstructions. So one attack has been to look at representations in these rings as the obstructions, so by Burgess, Rickenmeier and others. Then there has also been the geometric approach where the algebraic and geometric properties of the points y and x. For example, if y and x are forms, then the curvature of the the hypersurfaces and how they change under taking limits, that has been one approach. And now a wider class of questions have come up about orbits, closures, the moment map, optimizability and so on by Wigderson, Visu and so on. So really from our viewpoint, the from our viewpoint, so the stabilizer problem is really that you have a point x, and the orbit OX, and you have the point y, which is the larger orbit, and that there is a closure. Basically taking the leading term is essentially having a projective closure from y to x, a path from y to x, and the stabilizer of y is k and the stabilizer of x is h. So we would like to understand what is really the structure of stabilizers in the neighborhood of the orbit of OX. And so that is the structure part. And that how do these stabilizers change as you go from Y to this point X? So, understanding the path and how stabilizers change and how do we take limits in this Lie algebras. So one of the, of course, the lunar slice theorem gives us a very rich structure of the neighborhood of X. That is only when X is, of course, reductive and the orbit of OX is closed. And typically when X is our homogenized permanent, that is not true. So this part, I mean, this assumption does not hold. And about taking limits, of course, we know that if lambda t is taking y to x, then the stabilizers along the way are of course conjugates. But how do these limits happen really, and how does this k, the conjugate of k in the limit sit inside h? That is also not clear. So what we do is we build a Luna type partly factorized lower triangular model for non-reductive points. So it applies to all points x. We show that this model is computable, in the terms in terms of the representation row, and we connect it with some standard classical problems. We also show that the local model, as we call it, actually has quite straightforward connections with the differential geometry of the orbit, typically the curvature forms or the Gauss map. And we hopefully provide an entry into understanding how the deformation of the stabilizer of y actually works with h, and how does this deformation actually travel along the path from y to x. So hopefully, I mean, we provide some tools to understand the broader questions of which are posed by GCT. So let me now come to the first part, the local model. So the stabilizer question, that is how to describe the stabilizers near a given point. So Luna essentially for when the x orbit of x is closed and stabilizer of x is reductive. So the g action near x is really given. So this is there is this normal slice n, which there is a complement h action on n, and so really the GIT or the geometry of the G action near X is really encapsulated by the H action on N and then the quotient G mod H, right? And there's also a factorization of action that the H acts sort of vertically and the complement of H, sort of acts horizontally. And there is this separation of the two actions locally. And that tells us that the stabilizers within the vicinity of the orbit of OX up to conjugation actually lie within the stabilizer. So all K up to conjugation lies within H, and in fact K is the stabilizer of a particular point in N. So this is the Luna answer. Right, but of course the difficulty in extending Luna is that when we have a general edge, there is no such normal slice by which to take quotient. One candidate is to use V, the ambient space, quotiented by the orbit, so V upon TXOX, which is an H module, and construct GX, the Luna, the associated bundle. But that will again produce something where this slice, if I look at this map, GXHV, that map will, this is not quite accurate because it will produce an n bar, which is H invariant and which is actually not true. So the only map which holds in this connection is the GXHV, the associated bundle with V as the fiber, mapping to V. And this is exactly what we use to construct our local model. But note that this GXHV has a non-zero dimensional fiber. Unlike the Luna case where the dimensions match, here there is a big fiber. So let us just build the local model quickly. So the local model really is a reparameter. So it's, first of all, it's a Lie algebraic model. It's not a Lie group model. And it essentially is a reparameterization of the neighborhood of V. So what we do is, we choose M, a subgroup, a submanifold of the group G, to simulate the orbit, and we take N, which is a normal slice at the point X to the, to the tangent space, so to the orbit. So just to clarify how M is chosen, so we take the Lie algebra G of the ambient group and H the stabilizer of the point and S as its complement. So this S and we take the manifold so that it's at the origin the tangent space of M is actually S. So in a way we have taken a local complement, a manifold which is a local complement starting at the identity, and we have named the tangent space of that manifold S as a complement to H. Now this S is going to play an important role. So by this choice, what we have is that M dot X. So if I look at X and apply M to it, it is in fact the orbit, right? We are going to get locally the orbit, right? But M dot X plus N in the neighborhood of this point, M dot X plus N is nearly the same dimension as M dot X, right? And it is transversal to N. So that's all we can say. The orbit of X plus N may be much larger than M, because the stabilizer of X plus N may be much smaller and M may not be a complement. So what we really have is the decomposition of the ambient space here, Tf of X as S dot X plus N plus the complement. So we have this, right? So essentially what we have is, in this neighborhood there is a uniform parameterization, of the tangent space by S and by N. So our model is really mu of the M cross N is just that given M comma N, it just goes to M dot X plus N. So when M is the identity E, then this is just X plus N, the normal plane. When X is when N is zero, M dot X is just the orbit. So it's sort of a cross product of the orbit and the N. So this is clearly a local diffeomorphism, but it doesn't have a G action yet. So what we do is that the safest way of giving a G action to this is to embed, I think this should be M cross N, M cross N, is to embed M cross N into into an equivariant map, a G equivariant map between two spaces, right? And inserting this M cross N into this in a transversal manner, transfers to the fiber, and that itself allows us to define a G action on this M cross N. And the G action is very simple. Take the G action on X and just split it into along the fiber of this G equivariant map and in the tangent space of M cross N. So the Lie algebra quotient can be constructed very easily just by taking transversals to a fiber map, is really what allows us to put a Lie algebra action on M cross N. So here is the map. So here is our M cross N, and and what we do is we look at GXHV to V, and just immerse this M cross N into this. You can count dimension. There's the right dimension, and at e comma 0, that's at the point X, it is actually transversal, and everything works out. So this is the local model at the point. So really, I mean, so this gives us an action of the Lie algebra on M cross N, right? And which is equivariant, which is a model which is in the neighborhood of X. It maps accurately what is happening in V. So let us now show that the action of this of a typical element of G on M cross N is very special. So note that the action is very simple. You allow the M cross N is embedded inside M cross V. Just take the action of the Lie algebra element on M cross V and restrict the tangent vector at that point to the tangent space M cross N. So in this picture, this is the G action at the point, and this is the decomposition along the fiber and across the space M cross N. So that's the way we build it. Okay, so so we have said that this is how we define. So here is the actual Lie algebra map. So I mean, I will just explain it. So note that if I have the Lie algebra element G, which is the sum of H and a complement element H plus S, we act it on E cross N, right? So E cross N is the point X and X plus N. Remember that E goes to X, and E comma N will go to X plus N. So we are really computing the action on this slice. After all, since this slice moves around, if I compute the action on this, it would be adequate. So how is the action? Well, this is the associated bundle action given G on M cross V. Then the S part, moves the horizontal part, the first coordinate, and the H part moves the H dot N. So this is really the old associated bundle construction, right, on M cross V, except that it is in Lie algebraic form. Now if H dot N is actually along N, right, then there is nothing. Then you don't need to do anything, because this is already, this vector S comma H dot N is already in the tangent space of M cross N. So that's fine. But if it is not, if H dot N does not lie within N, this vector, then we have to project it along the S part and along the N part, right? So we have this projection lambda. So here is the final action. So I solve H dot N equal to S prime X plus N prime, right? So there is a vertical component and a horizontal component, and then the action is this G dot N equal to S plus S prime, this part plus the S part coming from here, and then the N part is this lambda N is the N prime, and this is this is the S part. So this defines the action of this is the action of G on this slice.
Milind, may
Okay.
I ask a question?
Yes, please.
Can you explain where this projection comes from?
This projection is actually you see, we know that S dot X plus N and N cover the tangent space V here. So S is a chosen complement, correct? So S dot, just as S dot X and
But
n are
that, sorry,
complementary.
but that decomposition you had chosen at the point X rather than at some other point. So
No,
I'm
correct. So
confused about.
this is lambda s n. So this projection depends on n right now.
All right, go on. I'll try to understand.
No. I'm just saying this lambda s n is the projection, is the decomposition at this point. So just as s dot x and n are complementary at this point, so are they at the point x plus n.
I see. Okay.
So therefore, this projection, what is this projection in terms of the projection at x? That is the key. That is what I will explain in the next part. But in principle, there is a projection, given any vector, it can be split as s dot x plus n and, something along the n part. So I obtain this projection and I obtain this action. So this is how the action looks like. So I think one should compare it with the Luna action. So given the element, G, which is H plus S, so the S part really just acts on the horizontal part, right? It has no vertical component. While the H part, we will see if it has a Levy decomposition R plus Q, then it acts on the vertical part, and it has a horizontal component, which actually we will see later. Depends not on H, but in fact on the the nilpotent part of H. So really, it is in that sense this action is block lower triangular, right? So while you see in the Luna case, this Q would be 0, and it would just be a block diagonal matrix where the S part will act on the S part and the H part will act on the N part, and and all the we have those happy stabilizer conditions. But the upper triangularity also has very useful computational advantages. So if I want to compute the stabilizer of E dot n, say if I want to have that G dot E dot n equal to 0, then we have that lambda n of Hn must be 0. Okay, so that is the stabilizer condition. So if I look at Hn as all H such that the projection is 0, that is that is one thing. So given that this is 0, I plonk it into here and I match it with I complement it with an S, right? So essentially, just as an upper triangular solution, I first solve this equal to 0, then I will get this, and then I use S to cancel out whatever is this effect of lambda s h dot n. So really, I mean, what we have is that this h dot n, every element of h dot n will give me a stabilizer in of G. So so what we have is that given any h, given any element h and the point n, there is an S completion. So there is a unique element S which is given by S equal to minus of lambda s h dot n, right? And if I complement this h with that S, then I get a G where G dot n is 0. So in principle, the solution of the stabilizer, the stabilizer is really in terms of lambda n and the action, the old action of h on n, which need not preserve h, but it may have some n part and some s part. So what we really have is that all the stabilizers at x plus n, at any point, at the point x plus n or y for that matter, every element which stabilizes the point y can be split into something which stabilizes this part and something which complements the horizontal part, right? So we have that given any point, given the point y and stabilizer k, there is a subspace Hn, linear subspace of the Lie algebra of H, whose S completion in the above sense actually gives me K. So this is so this tells you that how to actually compute the stabilizers in the vicinity. So note that reductive algebras may appear in the vicinity of nilpotent algebra. So H may be nilpotent, and yet because of the addition of this S part, you get a semi-simple element, and you get something which so you'll actually get reductive algebras in the vicinity of nilpotent algebra through this S completion. And the main point is that all points on that slice, the stabilizers K, have really a corresponding equal dimensional subspace H, right? So there's a sort of there's a faithful map of stabilizers on that normal slice to subspaces of H, right? And the map of H completion. So this is really just the simple local model. And then, I mean, so as Nitin said, how do I actually go from the lambda n to, I want to do the projection based on the projection at the origin, at x equal to 0. So really what, I mean, I think that the trick there is that one must, if I look at look at S is both, S gives me, if I look at the tangent space at the origin, that is at x, then I should equate it both as an element of V as well as a Lie algebra element in the complement S. So it has this dual role, and this dual role, I mean, if I define this, I have to do some more, define this theta. So this theta is actually the transfer of the decomposition at the origin, that is at x, to x plus n. So we have a map theta n, which is a map from V to V, which is linear in n, right? Which helps you then the lambda n at the projection at the point n is nothing but the projection at n with this map 1 plus theta inverse before it. So this gives you what the projection operator is. So and the good part about this projection operator is that it is intimately connected. I mean, basically, if I look at the equivariance of this theta, it has very nice properties. So if I look at H, which has some Levy decomposition, R is a reductive part and Q is the unipotent part, and I choose S, N, which are sort of R invariant, then you will see that this theta is really coming from an R equivariant map from V cross N to V and S cross N to S. And in fact, if you look at this S cross N to S, it is a map from S is of course the orbit cross N to orbit, and R equivariant map. It is essentially, it is like the Gauss map. So if you have the orbit at the point X, if I move along, if I move along in a particular direction S, which is a tangent vector, right? And then how does the N, how does the normal move, in that, how does the projection of the normal to the tangent space? So this is really something like the Gauss map. In fact, one can show that, this map, this algebraic map phi, is really the curvature form, the S cross S to N, if you have orthogonal or some reductive group representations. So the data, so the local model actually has connections with the curvature form of the orbit at the point X. So so this completes the description of the local model at that point. So if we just compare what is going on, so what we see is that Luna, we have a G action and the H action on N. Instead, now we have an H action through, which is sort of which is twisted by lambda n and theta. Then we have a horizontal action. Here again we have horizontal action. Stabilizers are in H, while here we are stabilizers are really S completions of a corresponding subspace of H. So this is valid for good orbits, while the local model is valid for everything, except that it is of course a Lie algebraic model. So this finishes the local model. So let us now apply this. Let me pause. Any questions? So essentially, it's a block upper triangular. If you compare it with Luna, what really happens is that the unipotent part, the Q part, the Q part of H is really what is producing the shear, and that can be captured, and that is captured through this mechanism of theta. So let us just apply this to form space. So we have what we have is forms. We have a form F and a one parameter family AT, which is acting on this forms, and and it decomposes this into its sort of power sum, and where G is the leading term. So by the way, this AT is more general. It is not necessarily a one parameter family. It is any polynomial substitution in the variables of F. In F will produce will split the polynomial F into powers of T, and then G is the leading term. So I will say that G is obtained as a limit under the family AT of F. So by the way, I mean, at least in form space, all elements in the projective closure are actually obtained in this way. So this is the most general way of obtaining projective closures in the form space. So let us look at this example. So, really what is happening is that I'm starting from this form F, and I'm going to the form G by a path which is by a point, by FT, right? I mean, FT is moving it. And if the penultimate form is FB, then sort of the tangent of this path is FB, right? So this is the point G, and my path is approaching via the tangent, and the tangent is FB. So this is the scenario, and we already know that, we know that this each of these points has a stabilizer KT, and that is slowly changing. And for each KT there is also an HT, because this KT is nothing but an S completion of. So we'll just try to observe what happens as we move from here, from FT as F, from F to G. So there's some standard transversality assumption that that this path is not sort of tangentially coming into the orbit at G. So then what we have is that so we construct a uniform basis. So we know that there is KT, the stabilizer of KT is just a conjugate of the stabilizer K of the F, which is nothing but AT0K, AT0 inverse, just the ordinary thing. And that the dimension, I mean, everything, all of them are the same dimension, and that each of these KTs have an HT, right, whose S completion is the stabilizer. So we know that. So what we do is we give a uniform basis for KT, right, and which in the limit goes into H, right, and it goes into H and gives us a algebra K naught, which is actually a subalgebra of H. So what really happens is that the HT in the limit actually enters H and becomes a subalgebra, right? So that's how the transition really happens. So here are the key propositions. So given this KT, the stabilizer, of an intermediate point, I can produce a basis, K1, K2, KIT, of which is a polynomial basis, where the coefficients are in H and in S, and that the coefficients of S, the complement, have a bigger power, have T to the B, and this T to the B really comes from here, that T to the, remember that, this is the point X, this is the point Y, and this is N, and N has an associated power T, and that is seen by this S completion. So really this SI of T is nothing but the S completion of HI of T, right? And that T to the B is coming because, as we go closer and closer, the S completion becomes, the requirement of S becomes smaller and smaller, right? I mean, just applying the local model to this, in just carefully looking at the degrees. So we have this, HT is just this space, the linear span of this, and we know that at HT, as T goes to 0, the space K0 is nothing but, this basis taken at 0. It in fact, it is fully in H, and it is actually a Lie subalgebra of H. So this standard basis gives us that, these HTs in the limit at H0 is actually a Lie subalgebra of the stabilizer of G. So this and this also gives us, we can also see that this, there are some additional this K0 is also the stabilizer of the tangent. So if you look at this, the FB, so we have that H, the H acts on the normal, the n bar, the quotient, and that this K0 actually, this K0 actually is a stabilizer of this tangent. So these are very very useful conditions. So what we have, so when we apply to the determinant versus permanent, we see if this is the stabilizer of the determinant, this is the stabilizer of the small permanent, and if the small permanent actually appears as a limit, as a leading term, then a smashed version of K of the same dimension actually sits inside H, right, and is the stabilizer of a particular element, in FB bar in this GXHN module. So what we really show is that this GXHN bar, this is infinitesimally in near the orbit. It is actually, because the horizontal shear, in this GXHN bar is 0, and this is what is really happening in the general case. I mean, in the absolute epsilon vicinity of the orbit. So this is the application, the wrap-up theorem for what happens under one family, under a one parameter family. The simplest case, of course, which is important for GCT, is when we have a very simple one parameter family, just 1, 1, 1 and t, 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 right? Under this case, basically this is, it just implements a singular substitution. So if I have a form F and I want to substitute a singular matrix, for X, then one can easily implement it by this form. And if whatever is G is really nothing but the, under this substitution, the leading term. So this, if the family AT is of this form, then there's a grading which is available, and the whole Lie algebra gets graded, and we have many other, H itself is graded, and K naught is also graded. The smashed version of the stabilizer of the point Y, which is sitting inside X, becomes graded. And in fact, obtaining, so remember that K is the stabilizer of the determinant. So obtaining K naught in this case is very simple. You just express, it is just the leading term of, this is the weight decomposition of G. So take any element of the stabilizer of stabilizer K and look at its leading terms, and that is exactly what happens. And there's also the special element, Lie algebra element L, corresponding to lambda, which connects, which is actually connecting the form F with form G, and L normalizes certain very nice properties of L. L actually stabilizes G. So we have a very special element which conducts the whole procedure of going from the form F to form G, and this L is in fact sitting inside the stabilizer of G. So we have all these properties. So if we look at, I mean, just to, if you look at this, you see that this was the tangent of approach, but we also have the tangent of exit, right? So this is the tangent of exit, right? And one can actually ask whether the tangent of exit, so I mean, one can define the tangent of exit in this one parameter family case, and it is really, the one parameter family can give us this tangent of exit. And in fact, this special lambda. So what we have are that elements of the stabilizer. I mean, what we have is that there are elements of the stabilizer of the determinant, or that is of the form F, actually sit inside the elements of the stabilizer of G. All those elements which are of weight 0 vis-a-vis L. So this L, actually the grading of L sort of decomposes the stabilizer K, and if there are elements of pure weight in K, then those sit directly inside the stabilizer of G. So this is a very straightforward. I mean, that actually the stabilizers intersect. Have common element. So here is the more general form. Even when there are no pure weights, if there are semi-simple elements, then by some Levy Levy conjugation, one can reduce it to L weight 0, and we have the same structure. And in fact, for forms which are of codimension 1 in the orbit closure, some even more important structure theorems are true. So here is, if I apply to determinant, the 3x3 determinant, right? So so we know that there is an H, there is a K which is, I think, of dimension 16, right? So and so that also sits inside H, so of 16. So here is determinant, it sits inside of, there are 8 elements of weight 1. So I'm just listing all the decompositions here, and in fact we see that the forms, the orbit closures are Q1 and Q2. So if I look at the orbit of det 3, Q1 and Q2 define the orbit closure. Yeah, and there are actually stabilizers of the determinant which actually are stabilizers of Q1 and Q2. So what we said, that there are elements of the stabilizer of the original form which go into the stabilizer of the limit. So that happens because these elements are of weight 0 in L1 and L2. So this finishes the form A. Now I'll just quickly do the matrices and the conjugation projective closures. What happens if we apply this theory to matrices? So Bharat has done it. So in affine closures, it's very well understood. The Jordan canonical form actually does everything. But the question is that if I have a point outside the null cone, we know that the null cone are nilpotent matrices and points outside are non-nilpotent matrices. So if I have, for example, a point outside the null cone, which are the elements in the null cone it picks up? So that is an important question. So what is the projective closure in this case? So it turns out that it turns out that it is really the Krull-Schmidt the Krull-Schmidt dimensions of this point y. So if you look at the minimal polynomials and the fact if the minimal polynomial decomposition, which actually gives you the projective closures. So for example, if I look at the top nilpotent Jm, then it lies in the projective closure of only those matrices, if they're diagonal as a matrix, which have all distinct eigenvalues, right? So to obtain Jm in your projective closure for a diagonal matrix, all its eigenvalues must be distinct. So this, I mean, just to give you a so if this is my point y, which is not a null cone, so I have -1. The 2, 1, 1 is the signature of the eigenvalue -1, and 2 is the signature of eigenvalue 3. So if I just sum it up, I will get 4, 1, 1, and this 4, 1, 1 nilpotent matrix of size 4, 1, 1 is the top nilpotent matrix in the projective closure of this matrix Y. Okay, so as far as we know, we have not seen such a result. Of course, what the ordering of nilpotent matrices is known by Gerstenhaber, Hesselink, and many other people, and I think Constant also. But this connection between the non-nilpotent matrices and nilpotent matrices in its closure by this minimal polynomial type calculation, at least, is not. We have not seen it before. So this calculus gives you very simple ways of determining, what is closed under affine and what is closed under projective closure. And the structure of this, creating the normal space, the choosing the complement, it all works it's very computationally very precise, and one can actually, what is the map theta, which I had said, and how. So by the way, note that, we have chosen Jm. This is the point Jm, the top nilpotent. So note that in the top nilpotent, in the vicinity of the top nilpotent, are diagonal matrices whose projective closure actually gives you Jm. So but the stabilizers of the diagonal matrices and Jm are very different, and yet through the process of S completion you obtain all those things. So you can very computable notions of how to obtain the stabilizers in the vicinity. So I will not go into this. So I will how much time do I have, KV? 5 minutes or 8 minutes?
No, you have 15 minutes.
Oh, okay. So I'll just do some advanced topics. So I'll just give in 5 minutes. I'll take some time so that I leave some time for questions. So I think that that this limit of kt going to k0 is quite a tricky computation. You see, what happens is that if you look at the the S completions, they get smaller and smaller as you go approach the limit, and eventually there is no S completion required, and you enter into the stabilizer of G. So this is how the stabilizers of the point actually enter into it. So the question really is that if I look at H plus epsilon, if I look at a point G plus epsilon FB, just a small point, just a thickening, epsilon thickening of the orbit, what is the stabilizer at that point? So so if I have a point G plus epsilon FB with epsilon square equals 0, what is the stabilizer of this, of that point? And that's probably a good model for KT, right? So so we would like to understand in that infinitesimal, in the infinitesimal thickening of this orbit, what really are stabilizers. And they are, so my simple way would be to assume epsilon square equal to 0, and then basically you get some derivations, right? And and what it reduces is to the question that is there something, this k naught is the collapsed version, is there something which is an epsilon thickening, which are the same c epsilon dimension, but which when I put k epsilon equal to 0, I get k naught. So is there a sort of epsilon lift of this k naught which is simulating this kt? So it turns out that this is really a sort of a extension of derivations of Lie algebras, and the extension of derivation under certain conditions is equivalent, or rather, if this extension is coming from if there is a family kt going into k naught, then there is such an extension, right? So if indeed kt is coming into k naught, then this extension problem is true, that there is an extension. So in the sense that not all subalgebras of k naught or subalgebras k naught or h are good limits of these one parameter families. They need to also be extendable. This derivation needs to be extendable, and that gives us some Lie algebra cohomology conditions, right? And which are also expressed here. So that is one part. The second part is more exploratory, right? So what we have seen is that there is this point y, and we are looking at projective orbit closures, right, of this y. You see, and that these closure forms may be of different codimensions. So there are codimension 1 forms, there are codimension 2 forms, and so on, which lie in the closure. And there are these ways of approaching one parameter families by which we exit these, and we get some leading term, and that's how we obtain these limits. So really, is there any way of of course the one parameters family lambda correspond to the Lie algebra element L, right? And so and the exit tangent of exit at this point. So I think that, is there a geodesy of these paths? This such an analysis is important for Kempf as well. So is there a local differential geometry of the point y? We already know that this theta and so on business, that there is the local differential geometry is connected to the algebra of the problem. So we would like to know whether there is a nice selection of an exit, right, which will take us, which can measure where we will end up finally. So really, it's in the determinant versus permanent problem, it is really that the stabilizers of if I look at the determinant and the orbit of the determinant and the action of the stabilizer of the determinant on the tangent space, then special directions of those, so we have already seen that that action has many stabilizing elements which actually go here, right? So we already know that there is a connection between the stabilizer of the determinant and of this action over here coming leading to stabilizers here. So really, is it possible to predict by looking at the direction of exit what sort of point are you going to end up at? So this is what that section 9 of the archive paper tries to address. So I think there are many sort of open questions or interesting questions which I will not go into, but they are there. I hope they are there. But I think I think that one important point which I'm trying to look at is that how do limits actually gather stabilizing elements, right? If y is going to x, then certainly the one parameter which is taking y to x becomes a stabilizer of x. So are there, how does x actually gather stabilizers, stabilizing elements? Are they really coming from limits? These are some of the questions which we should work on. And basically, are these cohomological conditions effective and salient? And of course, the Kempf's one parameter. So are they really optimal paths? So these are some of the questions which we would like to work on and strengthen the kind of tools which are available to solve this permanent versus determinant problem. So let me stop here. Thanks. So I'm done.
Thank you. Thank you very much. Are there questions?
Can I ask one, Milind? Nitin.
Yeah.
So you use the linear structure of V powerfully to make your decomposition.
Yeah, Nitin, is that Nitin?
Yeah.
Yeah, can you speak a bit louder?
I'm saying you use your linear structure of V to make your projections and decompositions. Isn't that so?
Correct.
Yeah. Now for more differential geometric things, perhaps a Riemannian metric, maybe, meaning if your representations are orthogonal, perhaps you can say more of the differential geometric kind.
Yes. So yes. So I think that much of the even if the even if they are reductive, I think some things can be said. So just the existence of a bilinear the bilinear form, which is invariant, may itself help. So, for example, in the case of the determinant, the stabilizer determinant is reductive. So the local differential geometry of the orbit at that point perhaps can be computed. I mean, what we need is a invariant bilinear form.
Yes.
Positivity, is it required? I'm not so sure. I have not thought about it deeper.
All right. That's an important distinction. Yes. Yeah. Reductive may be enough for you.
Okay, thank you. Are there other questions? So I will ask my two questions. So I have one that I actually I missed the last few seconds of Bharat's talk, and so I sent him an email with a question, but maybe I ask you also. The Luna model and the local model, they look, at least from very far away, like a cross product construction. Is there a formal connection between those?
Yes. So in fact, that's what I said, that the Luna actually gives you, I will just show it to you here. So the Luna, where is this? Yeah, the Luna is actually a block diagonal construction, right? That the S part just, so what Luna does is break up the Lie algebra into H and a complement S, okay? And then the S part really operates horizontally along the orbit, and the H part operates vertically along N. And the two stay separate, at least on the slice, on the normal slice. While our local model, since this N cannot be found, it is block upper triangular, right? And so, a system which is block upper triangular is nearly as easy as a system which is block diagonal. And that's where, and that the block upper triangularity is coming from this Q part, which is the the nilpotent part of the algebra. So indeed, they are very similar, except that it shows you that why that Luna thing cannot really work, because of this horizontal shear.
Okay. So thank you. The other question is actually, so when you went through the slides very quickly, I've seen, so I don't think I saw it during the talk, but there's something about the two co-cycle.
Yeah.
Can you explain a bit about this?
Yes. So I'll explain. So there has been I'll just go here. Yeah. So I mean, this formula. I mean, you see the formulation. This formulation is really asking whether what subalgebras of the stabilizer of the permanent, or H, what stabilizers of H are actually coming as limits, right? So that is the question. And what we have said is that if they are coming as limits from KT going to K naught, then there is an epsilon thickening of K naught, and that gives you this sort of condition, right? This sort of so that, I mean, if you look at it, it becomes it becomes a question of extension of derivations, which is really sitting in one co-cycle. So it is of H1, while it borrows from Nijenhaus and Richardson, which have a slightly different formulation of the problem. I mean, the problem which they have is slightly different, and there it comes from the two co-cycles of it's basically a Lie algebra extension problem for them, a subalgebra extension problem. While here we have it's a slightly different problem. So we seem to be looking at H1, while they seem to be looking at H2. The other point, if you look at the archive paper, is that this also has some direct connection, I think, with if I'm looking at codimension 1 orbits, closures, then whether they are one parameter subgroups or they are special, I think it has some connection with that also. So the two co-cycle is what Nijenhaus and Richardson, their problem needs, where I think our problem needs derivations which are really one co-cycles, or one, they are basically one alternating forms.
Okay, I understand. Thank you.